Today we're going to talk pretty briefly about electric fields. We're going to go over what they are conceptually and how to draw them, and then we'll get into the actual math next time. So before we can get into electric fields specifically, we really need to talk about what a field is. So fields are physical quantities that have a value for each point in space over a defined range, which sounds like a bunch of complicated mumbo jumbo, but what it really means is, say you're looking at this area right here, that every point in that area is going to have a value for something, and we'll look at a concrete example of that here in a second. So there's several options for what that value can be. The type of value, there are scalar fields where every point has a scalar value associated with it, and there are also vector fields where every point has a vector associated with it. One example of a scalar field is a temperature map. So you see these commonly on the weather, and here's an example of one. So everywhere throughout this region, southwest US, has a specific temperature associated with it. And temperature is a scalar. It's just some numerical value with no added direction or anything like that. So you can see on the map, they have used color to represent these values, and there's the scale up here. So values that are more in the warm tones are warmer temperatures, and values more in the cool tones are cooler temperatures. So you can look on the map, and for each point, you can see the color, and you can find that color on the scale, and you can associate a value with it. So every point on this map has a temperature value. That set of values is called the temperature field. Another scalar field type is a topographical field. So topography is kind of mapping out terrain and its elevations. So here's an example of a topography map. You can kind of see this little piece of landscape, and over a predefined area of ground, like this area, there is an associated value for height at that particular X and Y coordinate. Here they have also used color to depict that. You've got the higher areas in green, the lower areas in a darker blue. But you can see every point has a height, and that height is shown here in 3D. So this was actually a Python simulation that was run where they took height values for X and Y coordinates and used that to generate a map. You can also have fields that are comprised of vectors. So every point is going to have a magnitude and a direction. One example here also comes from weather, and it is a wind flow. So you can see at each point on the map, there is a vector, and obviously they can't draw in all the vectors because that would be, crazy. But you can see at regular intervals the vectors. They've got longer ones where there's more wind, shorter ones where there's less, so that's showing the magnitude. And you can also see the direction, so you can kind of see the general pattern of the wind flow. Electric fields, which we will be studying, are also vector fields. They basically kind of map out the force to charge ratio and the direction that it's going to go. So we're going to take a quick look at an electric field in simulation. So you can find the link to this simulation. It's just a PhET simulation in the slides, or you can Google PhET charges and field simulation. It'll pull right up and it'll run in your browser. So essentially what an electric field is a mapping at every point in space of the force to charge ratio due to a certain charge distribution. And when we draw these fields, we are assuming we're using a positive test particle. So that means we're looking at the force to charge ratio of this charge on a positive charge. In this simulation, we can use these sensors as our, quote, test particles. So the size of the particle doesn't actually matter here because we're doing a force to charge ratio, and we'll look at why mathematically that works later. So what you can see as we move a test particle around is the vector is the force to charge ratio. that the central force is exerting. So if we pull the test particle really close, that force gets really big, which is consistent with Coulomb's law that we know. And if the force gets further away, it gets really small. So as we move it around, we can see the vector growing and shrinking in magnitude. But what also changes is the direction. So as we move the particle around, the direction is constantly changing so that it is always in the opposite direction. It's being repelled away from that force in the middle. And I apologize, I just rewatched that little piece and see that it's not moving smoothly because of the way this app records. So go play in the FET yourself, and you can make it move more smoothly. Now where this gets a little more interesting is when we add other charges in. So if I add a negative charge somewhere, that completely changes the field. So now all of the vectors look different. So if I put my positive test charge right in the middle of the two, it's definitely going to be pointing away from the positive and towards the negative. But I can see that change over here on this side. So here where it's closer to the negative than to the negative is pulling more than the positive is pushing. So the net force is towards the negative. And as I get closer to the negative, that's even more true. So electric fields are super useful in gauging the trajectory of a particle rather than just its acceleration or the forces on it at a particular spot. Because without electric fields that are already mapped, every time a particle moves, you'd have to continuously calculate the new force. But with electrical fields, you can see that trajectory without constant calculation. So now that we kind of know what an electric field looks like, we're going to talk about the field model. So we've already talked about the charge model. The charge model says we've got positive and negative charges, and they exert forces on each other, where like charges repel and opposites attract, and that the force changes over the distance. That's the charge model. Now the field model states that a group of charges, the source charges, just some group, alter the space around them by creating an electric field. So we saw that that was definitely true when working with the simulation. We could see the space around the charges not as being of empty space, but having a net force that's already associated with it. And if a charged particle interacts with the field where there is that net force, the charge is going to experience the force. So one of the things that gets people hung up about electric force and gravitational force is that they act over a distance. So the field model claims that the mechanism for acting over that is that each charged particle and each massive particle generates a field around it, and that field is what causes the force on other objects. And there's actually a lot of research that proves that electric fields exist as a thing of their own outside of charge, because platypuses, or platypi, I guess would be the plural, platypi can sense the electric field generated by living beings as an adaptation for their survival. And it's also been measured, the electric field of the heartbeat being sensed by other muscles. So whereas the charge model just stated that one charge will have a force on another charge, the field model says that each charge generates a field, and that field is what causes the force. And this is also true for gravitational fields. Every object that has mass generates a gravitational field, and that gravitational field produces a force on other masses. All right, so your practice for today, after you finish all your Gross Coulomb's law, vectors, and math with weird units, your practice for today is drawing some fields. And we're just going to do this qualitatively, not quantitatively, just kind of eyeballing it. And to do so, you have to know a couple of rules. One of those rules is a convention. And the convention is that forces, or the force to charge ratio, the vectors in a field, are always going to point away from positive charges. So they radiate away from positive charges. Missed that one. And they go towards negative charges. So the way that we measure electric fields is by measuring the force on charged particles. So in working with electric fields, we always assume that there is a small test charge, and the size of this charge doesn't matter, which we'll see mathematically later, but the test charge is assumed to be positive. Okay, so we're looking at the force to charge ratio on a positive test particle, and that's why the field lines are away from positive, because positive is going to repel another positive, and they're towards negative. So let's practice real quick on a sample problem. We're going to see what the field would look like around two positive charges. And I'm going to do the field lines from this one, which we'll call 1, in red, and this one in blue, so that we can see the difference between the two. We're going to start with charge 1. So positive charges have lines going out away from them. All right, and as we get further away, these should get smaller because the vector is decreasing. Now, on some things like the simulation, they'll use light and dark for this. But I'm going to use smaller vectors because I'm not capable of doing light and dark right now. And you could add in more as you go, as it branches out, however much you need to kind of figure it out. So this is showing all of the forces, or the force to charge ratio, as we go outwards from that charge. And from the blue charge, it's going to look the same. They're going to start large, going outwards, and then they're going to get smaller as we go further and further away, which we know from Coulomb's law. But what we see is here in the middle, things start to collide a little bit. So here in the middle, we'll have vectors whose x components cancel out because they're pushing in opposite directions. And that's along the center line here. So if we can't have anything going in the x direction, we still have both going in the positive y direction. So up here close to the center line, all of the forces are going to be pointed upwards, and down here on the bottom, they're going to be pointed straight down because the x components are going to cancel and the y components are going to add together. And you can see if you add the vectors together as you approach that center line, that's always what's going to happen. Things are going to start turning upwards as the x components start canceling more, and the y components are going to get bigger and bigger. Okay, and then where it's not in the middle and it's way closer to one charge than the other, it's just going to follow that charge's lines more closely. At this point, I'm not caring about magnitude, I'm kind of just caring about direction. So far away from the middle, it's just going to look like a normal charge distribution. But here in the middle, the x components are going to cancel and the y components are going to add. And you can go check this in any sort of charge simulation. So I'm going to ask you to do a few quick little sketches as a homework. and that'll be in Google Classroom. You can use a simulation to check yourself, but please try to conceptually do it before you use a simulation. Thanks for watching, and let me know if you got any questions.